Hello everyone. Today I'm going to introduce how to represent graphs and a very interesting topic, graph isomorphism. All right, let's see the first way to represent a graph, which is called adjacency list. So let's see. This is the graph. So we can represent this graph by this table. So let's see on this table, adjacency list. It can represent a graph with no multiple edges by specifying the vertices that are adjacent to each vertex of the graph. For example, the vertex A is adjacent to B, C, E. So you can see for this table, when we list all the vertices starting from A, the adjacent vertex is B, C, E. And then next, B is also adjacent to A. So in the second row, B adjacent to A. And then for C, it adjacent to A, B, E. Okay, so we write A, B, E is the adjacent vertex of vertex C. So by using that, we can represent this graph by adjacent list. So you can also draw the graph by the adjacent list. Once this table is given, then we know totally we have 5 different vertices. So you can draw 5 vertices on your paper. And then we know A is adjacent to C, and we can add edges between A, B, and C, and E. Then you can draw this graph by this given adjacency list. For directed graph, we can also draw adjacency list because we can define the adjacency vertex with A, we have the edge from A to B. Okay, so in this case, we can see A is adjacent to B and C and D and E. So B, C, D, E. So in this case, we have vertex A to B, C, D. Here we have the loop in this directed graph. Okay, so maybe we can check what are all these adjacent vertices of vertex B. So B and B, right? Only 2 vertices. So for the second row, B is adjacent to B. So in this case, you only need to discover what is the initial vertex and what is the terminal vertex. And you can denote this adjacency list. Right? Next representation is adjacency matrix. So if we have a graph with n vertices, you want me to be n, then the adjacency matrix, the dimension will be n by n. And then we can use binary matrix 0 and 1 to indicate if we have the edge between vertices I and j. So next we can see the entry Ei is defined by if we have an edge between Ei and Bj, then the Ij entry of this matrix will be 1. Otherwise it's 0. So let's see this example. If we have the graph ABC here, then remember the vertex number is 4. Therefore, we have the adjacency matrix with the dimension 4 by 4. And then we can see if we have an edge between the vertex I and Bj. So take the first row for example. We verify if the vertex A has H to ABC. So in this case, A has the H to B, C, D. Okay, so in this issue, we have 1, 1, 1 here. Right? Next, let's see for vertex B, it has H to A and C. So for vertex B, it has H, A, and C. We have 1, 1 here. For the other entries, they are all zeros. Okay, so this is the representation of adjacency matrix. So you can see it's different from adjacency list because we use the matrix n by n to represent a graph with n vertices. Okay, next you can see when we have sparse or dense matrix. For example, we call this sparse matrix. That means we have a lot of zeros in this matrix. If we have a lot of zeros, that means we have only a few edges of this graph. So in this case, if we don't have many edges, then maybe we can use adjacency list because it's not efficient to develop a very large n-by-n matrix with a lot of zeros. So once we have a lot of zeros, then it's more efficient to apply adjacency list. But if we have a very dense, so many edges, then we can apply adjacency matrix. Okay, the adjacency matrix can be applied to a lot of different problems because it allows to use loops and multiple edges in this graph. Let's see for this example, if A and B have multiple edges, multiple C is 3, then for the adjacency matrix, the entry A into B is 3. Because we have 3 entry A into B. Right? It can also represent the loops because for C, we can see C actually connect to B, E, and C itself. Okay, so you can see if we have a loop for C in the entry on the diagonal, the entry 3, 3 will be 1. That means we have a loop for vertex C. Next, let's see the directed graph. We can also apply adjacency matrix for the directed graph. Once we have the directed edge from Vi to Vj, then we can become 1 for that entry. Alright, so maybe let's try this graph. How to develop adjacency matrix for this directed graph. Because it follows the same rule to the previous graphs with multiple edges and loops. All right. Have you finished your answer? First step to determine the dimension of this matrix. So here we have A, B, C, D, E, 5 vertices. So what's the dimension of this adjacency matrix? All right, one extra point if you can draw your graph on the blackboard. Okay. Okay, thank you. Let's verify. Once we know there are 5 vertices, then we have the 5 by 5 adjacency matrix. Let's verify if all these entries are correct. For the first row, A has the relative edges to B, so for the vertex A, we have 1, 1, 1, 1 for B, C, D, E entries. Okay. For B, we have a loop for B. So we connect to B, E, only, right? Because we have only 2 directed edges using B as the initial vertex. So B, B. How about C? Okay, for C, we have H, C, and A. So for C, we have ACE. That all these entries are 1. And then for B, right, there's no edges as little edges. So we have all zeros for the first row. And then for vertex E, we have B, C, okay. So BCD is 1. Okay, very good. Let's see another representation, which is called incident matrix. Okay, once we have the graph G, then we have V1 to Vn n vertices, and we have E1, E2 to Em m edges. So the incident matrix will be n by n. Okay, once we have V1 to Vn n vertices, and we have E1 to Em n edges. And for incident matrix, the dimension will be n times n. All right? And then the definition for each entry in IJ, if we have HEJ incident with I, then we give a 1 for that entry. All right, so let's check this example. If we have the graph V1 to V5, and then we label the edges P1, P2, P3, P4. So remember, once we have 5 vertices and 5 edges, then the dimension of the matrix will be 5 by 5. And then we can see E1, actually an incident with E1 and V4. Okay, so for the first column, E1, we have V1 and V4. This is 1. then for E2, it incident with E1 and E5. So E1 and E5, we E1 for this to be E2. So you can follow this sequence from E1 to E6. Okay, so eventually will be 5, 5, 6, 6. Then for each column, each edge incident by 2 vertices. So we have 2 ones. And that's the result of incident matrix. Next, let's see. Once we have pseudo graphs, okay, so that means we have multiple edges and loops. So let's see for E1. Actually, E1 is a loop page connecting E1. Okay, so if the first column is E1, then we only have one for V1 because the matrix the vertex E1 incident vertex is only V1. Okay, and then let's see V2. E2. Okay, E2 actually it incident with V1 and V2. So we have 1, 1 here. Okay, so now you know if in this loop edges, then we have only one in that column. Once it's just 4 edges, then we have 2 ones on that column. Right? So maybe we can check the property of this matrix because for incident matrix of simple graph, so the adjacency matrix will be symmetric because once we know A adjacent to B, that means B is also adjacent to A. So you can see the adjacency matrix for simple graph is a symmetric matrix. So if you observe by the diagonal, you can see we have 1, 1 here, we have 1, 1, 1, 1 here. So actually this matrix is a symmetric matrix. Okay, so adjacency matrix for pseudo graph. Okay, so you can see it is also a symmetric matrix, right? Is that symmetric? Because the entry between A and B is 3, and B to A is also 3. But for directed graph, it's not symmetric anymore because if we have an edge from A to B, then the entry of B to A, it could be 1 or 0. Okay, so it is not necessary to be symmetric matrix. Okay, so for incident matrix, it's not a square matrix, so we won't talk about if it is symmetric or not. All right, let's see another topic, isomorphism of the graph. Okay, so let's see this definition. If we have two simple graphs G1 and G2, we call that these two graphs are isomorphic if there is a one-to-one and onto function from V1 to V2. Okay, so that means A and B are adjacent to each one. Then after this subtopic function of A and of B are also adjacent to each two. So if two graphs are isomorphic, if they're not, we call that non-isomorphic graph. So maybe we can use this example to understand what is the definition of isomorphism. So here we have a graph here. So if you consider we have a board, and then we have 4 pins. You can put the pin on the board, and then attach some rubber band of position. For example, we switch the pin of U2 and U4. So you put the pin out of the board and put it in another position of U2. And then you also put this U2 to the position of U4. So if you switch the pin, then the rubber band will go to different directions as well. Okay, so if you can apply these operations, that means actually this graph is derived from the original graph. If you switch the pin, and the corresponding edges also changes. So that makes these two graphs are isomorphic. Because based on the definition of isomorphism, we can apply a one-to-one correspondence function. So in this case, we know U1 taken back to U1, U3, U4. Because once you switch to vertex back to its original position, it becomes the graph. So actually, you can apply this one-to-one correspondence to verify actually the same graph. So that is what we call isomorphism. Okay, so first thing we can think is how many possibility, how many different graphs we can try to verify if two graphs are isomorphic graph. Because we know it's one-to-one correspondence, so assume we have n different vertices, then you need to try if the first vertex of U1 map to U1, U2, U3, U4. Okay, once you can verify U1 map to U1, and for U2, we have three different candidates. So for U3, we have two candidates. In this case, if you have n vertices, then totally you can try factorial n possible one-to-one correspondence function. Okay, so you know it's very time consuming and the operation is very exhaustive. So next, I will introduce some simple rules help us to verify if two graphs are isomorphic graphs. We call this graph invariant. So what is graph invariant? So we already know that we only switch position of the pins and rubber bands. So we can check the number of vertices. If these two graphs have different number of vertices, actually you cannot switch the pin and rubber band to make it the same. Okay, so if the number of vertices is different, then it's not isomorphic graph. So does the number of edges or degree sequence. The degree sequence is the degree of all vertices, and you can sort in non-increasing order. Then you can check if the degree sequence of these two graphs are the same or not. All right, let's see this example. We have two graphs, G and H. So based on observation, you can see actually we just change the H to the position SW. So their number of vertices are same, number of edges are same. How about the degree sequence? Okay, so you can see the degree sequence also the same because we have degree 3, 3, 3, 3, and 2, 2, 2, 2. So the degree sequence will be 3, 3, 3, 3, 3, 3, 3. And for the graph H, we also have 3, 3, 3, 3, 2, 2, 2, 2. Okay, so the degree sequence for both graphs are also the same. Okay, so what else we can observe to distinguish? Because in this case, they are not isomorphic graph. Okay, so maybe we can see, actually we have the vertex x, y, and u, they are all vertices with degree 2, right? But for this vertex, they need to attach one vertex with degree 2. Okay, because for p adjacent to u, that's a degree 2 vertex. And for x8 adjacent to y, is also a vertex of degree 2. Then maybe we can check how about in graph G. This is a vertex of degree 2, but all its instant vertex is of degree 3. B degree 3. B degree is also 3. So you can see, actually you cannot map A to any vertex of degree 2 in the graph H because their neighbor with different degrees. Okay, that's one possibility we can check if they are not isomorphic graphs. And also we can see, actually we have a special shape here, WZS. Okay, but in the graph G, you cannot discover another because we have the right angle, for example, the large rectangle, the middle rectangle, and here we have another rectangle of the three rectangles. But in this case, we have the large rectangle, the middle rectangle, but we cannot establish third rectangle to match WZS. Okay, so maybe you can have a lot of different observations to help you discover if these two graphs are isomorphic or not. Okay, maybe we can also apply induced subgraph. Okay, because for this vertex of degree 3, actually you choose the vertex of degree 3 and its corresponding induced graph. Then you choose WBS and induce the graph. But you choose all these degrees 3 in graph G, then you will select BFHE. And you induce the subgraph of BFHE looks different from WZBS. Okay. If they are isomorphic, then you must choose induce the subgraph. But in this case, it is not. Okay, so we have so many different ways, or you can apply different graph invariants to verify if two given graphs are isomorphic or not. All right, next let's see this example if these two graphs are isomorphic or not. Okay, so we can see we have a rectangle here, and then we have a path here. So this path includes 1, 2, 3, 4, 4 vertices. So how about you draw this V6 out of here to make this one a rectangle? And then inside you will have one pass, V5, V1, V2, V3. That can correspond to U4, U5, U6, and U2. So remember, plug the pin, put it along here, and the corresponding edges. And you will have the corresponding rectangle in the path of 4 inside this rectangle. In this case, we can see isomorphism. So remember, when you prove these two graphs are isomorphic graph, you need to provide the one-to-one correspondence function, how to map each vertex in G to the vertex in H. All right, so maybe you are
so good at move the pin and the rubber band to discover if two graphs are isomorphic or not. But in this case, once we have many vertices and many edges, it's not that easy to determine if these two graphs are isomorphic or not. Okay, just give me your intuition. Do you think these two graphs are isomorphic or not? Raise your hand if your intuition tells you they are the isomorphic graphs. No? So, who do you think they are not isomorphic? Let's give it one more try. Raise your hand if you think that they are isomorphic. One, two, three, four, five. Okay. So raise your hand if you think they are not isomorphic graphs. Okay. Almost about the same numbers. Actually, the answer of this example is yes, they are isomorphic. Okay. So that means you need to adjust the position of all these vertices. Actually, you can move to the corresponding vertices in the graph, the first graph, and make it looks like exactly the same. All right. So next, I want you to try this exercise to determine if these two graphs are isomorphic or not. If yes, you need to provide one-to-one correspondence function. Otherwise, I'll give you your own reason. What kind of graph invariance you applied to verify they are non-isomorphic. Please write down your answer on your paper. This one is very easy, right? Okay, so if you watch this graph closely, you can see we have a rectangle here, and we also have a rectangle here. So how to make the other vertex in the first graph exactly the same to the second graph? If you can match the rectangle in the first graph and the second graph. So now you can see actually we have vertex 3 and 4, which is different to the second graph. So how about moving vertex 4 out of this rectangle and moving vertex 3 out of this rectangle? So if you move this vertex out of the rectangle and make it intersection here, and make this vertex out of the rectangle and make it intersection here, then you will have, if you can move out here, and you have the edge here, and you have to move the vertex here, you have something like here. And we also have edge connecting vertex 3 and 4. That would be the edge T5. Okay, then you will make the first graph exactly the same to the second graph. Therefore, they are isomorphic graphs. All right. So Now, do we have any algorithm to help us determine if two graphs are isomorphic? Actually, yes, but the time is very slow because we only have exponential worst case time complexity algorithm to help us solve this problem. So maybe you can check online to find the naughty programs. It can give you a very quick answer if the vertex number is below 100. Lastly, let's see the applications of graph isomorphism. Actually, we can verify if a new compound from the chemist of this synthesized compound are the same to the previous one. If you know the graph structure of that compound, then you can apply graph isomorphism to the new compound to the existing ones. And then we can also verify if electronic circuits they are the same to the original design. So we can use isomorphism for verification, especially for intellectual property examination. We can see if this circuit design is copied or modified from the previous one. All right, we have homework assignment, two problems in each section of 10.1 to 10.3, and the due date is in 2 weeks. All right, any question for this section? If no question, then we move to next section, connectivity. Okay, in that section, we will discuss the property of connectivities of graphs. So we will see different measurement, how we measure the connectivity of vertices within a graph. Okay, firstly, let's see what is paths, because we took a lot of about paths in previous sections. So now let's see the informal definition. A path is a sequence of edges, okay, that begins at one vertex and travel to vertex along different edges to the end point. Okay, so we call that a path. So the application of paths is a lot because if you remember the computer networks, so we can determine if we have paths for any given two vertices within the graph. Actually, it's a route we can determine is a message can pass from one bit center to another. All right. So the formal definition of paths, we have if the path is of length n, then we have the initial vertex x0 and we travel along s1, s2, s1 to sn. And then we will travel along edges e1, e2 to en. That gives us a path from a vertex u to vertex v. U is the starting point and v is the end point. Okay, so we define paths if we have simple graph and the path is denoted by its vertex sequence s1 to sn. We do not use h1 to the path. Instead, we use vertex s0, s1 to sn. And then we call the path is a circuit if we have the same start and end vertex. For example, we start from U and travel along the path and back to the vertex U. Then we call this path a circuit. And then when we build a path, if the path or edges is not repeated, then we call that is a simple path. For example, we have the path x0, x1, x2, xn. So the edges 1, e2, en is not repeated. So this is a simple path. But we may have another path, for example, x0 to travel e1 So E1 is travel twice. This is also a pass, but it's not a simple pass. Maybe we can check this example. Okay, so once we have A, B, C, F, E, okay, A, B, C, F, E. Okay, so it's a pass of length 4 because we have E1, E2, E3, E4, 4 different edges. So it's a pass of length 4. Next one, B, C, A. A, okay, we have no edges between B and C. Okay, so BECA is not a pass. How about BCFE? BCFE. Okay, so you can see it starts from B and ends at A. So this is the circuit of length 4. Let's go on A, B, A, B, E, E, A, B. Okay, so we can see for this pass, the H is repeated twice. So it's a pass, but not a simple pass. All right. Pass is very useful because in acquaintanceship graph, we know if people know each other, they are friends, then we can build the acquaintanceship graph. So the pass means you may know some person, and because you have common friends, so that build a relationship between two persons. For example, Kamini and Paula, they have a common friend, Jen. Okay, so actually you can discover the past of this graph to see how you connect to other persons. So if you don't know, if Kamini don't know the person Paula, maybe they can call his mutual friends Jen to introduce Paula to him. Right? So actually we have a very interesting theory. Actually it's not a theory, it's just conjecture. Okay. So everyone in the world actually may be linked by a small chain of this acquaintance graph by six, okay, by 6 people. Okay, for example, we have Kamini here. So if we travel a path of length 6 or 6 people, maybe we can connect Kamini to the chain because Kamini knows Jane, Jane knows Paula, Paula knows Tom, and Candace so this conjecture tells us actually everyone in the world, you can build a chain by 6 people to connect everyone, every pair of the person in the world. So we call this 6 degrees of separation. Alright, so actually this conjecture is um, based on this, we have a film that the actor is Will Smith. Okay, if you are interested, you can see this movie. 6 degrees of separation. All right. Another topic related to paths is the Bacon number. So in the Hollywood graph, actually, we have seen if 2 actors collaborate in the movie, we can build in this Hollywood graph. So if we have the center key person, Kevin Bacon, okay, then we can see what is the path or what the length of the path in Hollywood graph to Kevin Bacon. Okay, for example, our famous Jay Chu, actually he and Dennis Kiefer are in the same movie, The Green Hornet. And Dennis Kiefer collaborate with Kevin Bacon in Death Sentence. So actually the Bacon number of J2 is 3. Okay, so we can build everyone in Hollywood if they play any roles in the movies. Then we can see the big number one actually have more than 2,000 actors in Hollywood. And then we can see different big numbers. Remember, it's a lot. All right, next let's see the connectedness in undirected graph. Okay, so we call this graph connected if you can discover a path between every pair of the vertices. Then we call this graph connected. Take G1 for example. We have vertex A, B, C, D, F, G. Okay, so if any two vertices, for example, A, B, if you can discover a path in this graph, then we check every pair in this graph. If you can get a path for all pairs of vertices, then we call this graph connected. So let's see G2, which is an unconnected, disconnected example. Because you can see for the pair CD, you cannot discover the path. Therefore, this graph is disconnected. And then we can discover all this connected graph in this example. We can find all the connected subgraphs. Then we give a special name for this component, which is connected components. Okay, so in this case, we have H1, H2, H3 as subgraphs, which are connected components. So you can also call this connected subgraphs. Okay, so in this case, H is not a connected graph, but we have connected component H1, H2, and H3. Okay, that's a very basic understanding of connected, of how graphs are connected. Next, I will introduce some indicators to see how these graphs are connected. So the first term is cut vertex. If you can remove a vertex and produce more subgraphs, produce more connected components, then we call that vertex is a cut vertex. Okay, for example, for G1, if you remove a vertex, then you can produce more connected components. That means you make this graph disconnected. So maybe we can remove the vertex B. If you remove vertex B, then the corresponding edges are all removed. Then that makes A an isolated vertex. That makes G1 two connected components. Okay, so we call the vertex B is cut vertex. Actually, B is not the only cut vertex. C and E are also cut vertex. Because if you remove C and its corresponding edges, then we will have two connected components, A, B, E, and E, F, G, H. Okay, so if we have cut vertex, then we will have cut H. If you remove the H, and then you can produce more connected components. For example, if you remove this H, then this will be the first connected component. This will be the second connected component. So the HCD is cut H. Actually, you can also remove AB. Okay, because if you remove HAB, then A will be isolated vertex. Then you create two connected components. Right. Next, let's see a very strong graph, which is called non-separable graph, because it's a connected graph without any cut vertex. Remember the definition of cut vertex. You remove this vertex and make this graph disconnected. But we have some kind of
graph without any cut vertex. For example, we know K is a complete graph. Every vertex has an edge to all the other vertices. So once you remove one vertex from Kn, you won't produce any disconnected components. Okay, so actually you can remove 1, 2, 3, 4, 5 to n minus 1 until we have only one vertex left. You cannot produce more connected components. So we call this non-separable graph. All right, let's see the definition of vertex cut. Vertex cut is a start include all cut vertices in this subset. If we remove the cut, a vertex cut, the subset in front, then we can make G disconnected. Then we call this set vertex cut. So in our previous example, if we remove then we can produce more connected components. Okay, so BCE, if you collect them into a subset, this set is called vertex cut. All right. Next, vertex connectivities. The minimal number of vertices can be removed from a graph G to disconnect G or produce a single vertex. Okay, so that means if you have a graph, maybe you can try to remove one vertex. Then you can check if you can make this graph disconnected. If you cannot, then you try to remove two vertices. Then you try 3, 4, 5, 6 until you reach the minimum number of vertices. Once you remove all these vertices, you can produce more connected components. Then we call this vertex connectivity. We use a special character kappa to indicate the vertex connectivity. So we use kappa of G to indicate we need to remove how many minimal numbers of vertices to make it. Okay, so let's see we have two different conditions. Either to make it disconnected or you make it a single vertex. Because we know for complete graph, it's non-separable. So for Kn, we need to remove n minus 1 vertex to make it a single vertex. So the kappa of a complete graph Kn will be n minus 1. All right, this will be easy if you see this example. Okay, for G2, what is the minimum vertex we remove can produce a disconnected graph? Actually, if you remove C, then you will have two connected subgraphs. Okay, so the kappa of G2 will be 1. And then for G3, actually we can see we have A here. So if you remove B and G, then it will be disconnected. So for G3, kappa of G will be 2. Okay, so maybe you can try these two examples. What is the vertex connectivity? The minimum number you can remove the vertex to make it disconnected. All right. Next, let's see some properties of vertex connectivity. So if we have n vertices in the graph G, then vertex connectivity kappa of G will be 0 or n minus 1. Remember, kappa G is the minimum number of vertices to be removed to produce more connected components. So if the number is 0, that means the graph G is already a disconnected graph. So you don't have to remove any vertex to make it disconnected. So the kappa of G of disconnected graph will be 0. And then we already know that for complete graph Kn, you need to remove n minus 1
one vertex to leave a single vertex here, because it is non-separable. So the range of kappa G will between 0 to n minus 1. Alright? And then for K2, K3, the kappa G will be easy because it's complete graph. So you need to remove one vertex or two vertices to make it has only one single vertex. So lastly, we can have a new definition for K-connected graph. If a graph G, the vertex connectivity of graph G is larger or equal to K, then it will be a K-connected graph. That means you need to remove at least K vertex to make a connected. So we call this graph K-connected graph. Then, similarly, we can apply the same definitions for cut H, H cut, and H connectivity. So if you remove the H, you can produce more connected components. Then that H is called cut H. If you collect all this cut H into a subset, then we call this set H cut. And then we can also determine the H connectivity. What is the minimum number of edges you need to remove to make it disconnected? We use another notation, lambda of G. Okay, so let's see this example. For G1, is once you remove H, then we will have two connected components. So lambda of G equals 1. For G2, actually, you can see that the resistance of this graph is 4, 2, 2, 2, 2, 2. Okay. So the minimum edges we need to remove is 2 for example, the vertex F to be isolated. So lambda of G will be 2. Okay. So actually, lambda of G can be determined by the resistance and of this graph. And that will be the H connectivity lambda of G. Alright. Next, let's see the connectedness in directed graph. Okay, so we have two definitions of strongly connected graph and weakly connected graph. If we have a path from A to B and also a path from B to A for any pair of vertices A and B in this graph, then we call this the directed graph strongly connected. Okay, so let's see this example G. So for this graph, we have a path between A and B because we have a directed path. Use A as the initial vertex and B as the terminal vertex. And then we can also find another path from B to A. We can go from B, A. Okay, so in this case, we call it strongly connected graph. Right? And then we can also see the example of weakly connected if we have only a path between every two vertices with one direction. So in this case, we have B go to A. We have a path between this pair, but we don't have another path from A to B. So in this case, we call it weakly connected graph. Okay, so if you remember, we talked about computer networks in previous section, and we have introduced different network topologies. Okay, so now, right now, your answer. What is the network topology, which is a strongly connected graph? And what is topology is a weakly connected network topology. Or maybe I can give you the name correctly, we have the star topology, we have the ring topology, we have the wheel topologies for computer networks. And we talk about its reliabilities of these computer network topologies. Which one is strongly connected? Which one is weakly connected? So for the reasonable settings of maybe stars or rings, if we consider it is directed graph, so maybe we can send data from the center to all its terminals. And then we can also deliver data along one direction. And then we have the topology of the wheel. Okay, so maybe the last one. Okay, so how about your answer? How about you? What's your answer for these three network topologies? Which one is strongly connected and which are weakly connected? Do you understand the question on the blackboard? Because this is what we call star topology, ring topology, and wheel topology of computer networks. So can you determine which one is strongly connected, which one is weakly connected? Okay, so maybe we can check if this one is weakly connected. Remember the definition, for every pair of the vertices, we have only one path. Okay, so if we consider this one and this one, we have a path. Maybe we can deliver data between these two vertices using the network link here. Okay, so maybe we can consider we have a path. But once this path is broken, or we don't have another path, we can deliver between these two in the center. Okay, so we consider the star topology as weak connected. So how about the ring? Okay, so actually the ring, you can deliver from A to B using the path here. You can also deliver B to A along this path. Okay, so remember the definition. If we have paths between A and B, and another path from B to A, then they are strongly connected. So this one is strongly connected. Right? If this one is strongly connected, actually this one is also strongly connected. Because we have more strongly connections of this graph. All right? Next, let's see, paths can be also one possible graph invariant to determine isomorphism. Because for G and H, this graph, okay, so maybe we have the paths of 3 along V1, V2, V6 to V1. Okay, 1, 2, 3. We have a circuit of V1, V2, V6 to V1. But you cannot discover any circuit of length 3 in the path or circuit as graph invariant, then G and H are not isomorphic graph. Okay, so maybe you can try this example by yourself. Once you discover the number of paths, if we have path 3 and path 4, here, something like here, so it will be certain of 4. Okay, so actually, you remove vertex here and make a here. So we have a circuit of length 3 and circuit of length 4. Actually, you can match G and H to be isomorphic graphs. All right, we have the last topic in this section, counting paths between vertices. So here we have a very important theorem. If G is a graph and we have the adjacency matrix A, then the number of different paths of length R, we can actually calculate the adjacency matrix A to the power of R. So we can determine if we have how many number of paths between vertex I and J to see the entry on J. Actually, the number of entry on J just an instance of the number of paths of length R. Okay, so maybe we can see this example. If we have the graph G here, then we can develop adjacency matrix. Okay, and then once we need to calculate the path number of length 4 from A to D, remember by the theorem it tells us you need to calculate the adjacency matrix A to the power of 4 because we are trying to discover the path of length 4. So we need to discover the matrix A to the power of 4. And then we need to discover the entry A to D. So the entry will be A to D here. So once we know the entries 1 and 4, the number will be the number of paths of length 4. So in this case, we can firstly calculate A to the power of 4. So this matrix, then we discover the entry 1, 4, that means the path number between vertex A to vertex B. So the number will be 8. So that will be the number of paths from A to B of length 4. Okay, so we know the number is 8. So actually we can list all these paths of A to B. For example, A, B, A, B, B. So A, B, A, B, B is the path of length 4. So remember, this is not a single path. So we can repeat or travel from A, B, A, B, B to make length 4 paths. All right, so lastly is a proof to counting the paths between vertices. Why we can apply the adjacency matrix to the power of R to indicate the number of the length of the path of length R. Okay, so maybe I just leave this proof for you because if we prove by mathematical induction, this will be very, very easy if you can apply the counting rules when we have a to the power of plus 1. Actually, the counting hypothesis tells us we already have AR that is true. Then when AR times A actually is a series of multiplication and addition. And it will be easy to verify. Actually, it's the total number of different combinations of S number. All right. Any question here?
All right, if no questions, see you next time.